Welcome back to K11 Tech University. We've seen how powerful bit manipulation can be, right? Well, today we're taking that a step further with a truly elegant technique you'll find everywhere, from complex algorithms to the systems you use every single day. We're going to talk about encoding entire sets and all their possible subsets using just a single number. This is all about Bitmasks. So what's on the agenda? First, we'll kick things off with why we even need an alternative to the standard ways of handling sets. Then, we'll introduce the hero of today's story, the Bitmask itself. After that, we'll see how it makes set operations unbelievably fast, and this is the really cool part, how it unlocks a super simple way to handle every possible combination of items. And finally, we'll wrap up by looking at where this is used in the real world and the crucial trade-offs you absolutely need to know. All right, let's dive right in with the fundamental problem. So much of what we do in software at its core is about managing collections of things. Users in a group, permissions on a file, items in a shopping cart, you name it. And we're constantly asking the same kinds of questions, aren't we? Is this particular item part of this collection? What are all the possible combinations of features a user can have enabled? These aren't just abstract ideas. They are literally the core questions that thousands of algorithms are designed to answer. Now, you're probably thinking, hey, we've got tools for this, and you're absolutely right. Arrays, hash sets, those are our daily drivers, and they work great. But what if I told you there's a very specific, very common scenario where the total number of possible items you can choose from is small and doesn't change? In that case, is there a way to be dramatically more efficient? And the answer to that question is a resounding yes. This brings us to the Bitmask, a surprisingly simple and elegant idea where we can represent an entire set of items using nothing more than a single number. So what in the world is a bitmask? Well, it's just a number, an integer. But the magic is how we think about it. Imagine it's a row of light switches. Each individual bit, each 1 or 0, is a switch that tells us if a specific item is in our set or not. A 1 means the switch is on, the item is there. A 0 means the switch is off, the item's not there. Simple as that. Okay, let's make this real. Imagine our universe of items only has 4 things: A, B, C, and D. That's it. We just assign each one a permanent slot, or a bit position. So A gets the first slot, which is bit 0, B gets the second one, bit 1, and so on. This mapping is fixed. It never, ever changes. And this is where it all clicks into place. The number 0, right? In binary, that's 0, 0, 0, 0. All our light switches are off. That represents the empty set. The number 1, or 0001 in binary, means only the first switch is on. That represents the set with just item A. Now check out the integer 5. Why 5? Because in binary, 5 is 0101. The first and the third switches are on. That perfectly maps to the set containing A, C. Suddenly, every integer corresponds to one unique combination of our items. And that's the key takeaway right there. All the complexity of a collection, what's in it, what's not, is boiled down into one single simple integer. One number represents one unique subset. It's just incredibly concise. But this conciseness isn't just for showing off. It actually unlocks a massive performance boost. This brings us to set logic at light speed, where we see how bitmasks make common set operations ridiculously, almost unfairly fast. This is where the real magic happens. Just look at this. Checking if an item is in our set, that's a single bitwise AND operation. Adding a new item, that's a bitwise OR. Now, why is this so amazing? Because these bitwise operations are things the computer's processor does directly in its hardware. They are literally among the fastest instructions a CPU can possibly execute. Comparing 2 entire sets is now as fast as comparing 2 numbers. It's not just fast, it's constant time, meaning the speed is the same whether your set has 2 items or 20. The implication here is just massive. We've taken abstract ideas like union and intersection and translated them into the fastest possible operations a computer can perform. Our code becomes not just blazingly fast, but also incredibly predictable. But raw speed is only half of the story. Maybe the most powerful application of this whole technique is in the world of combinatorics, that is, dealing with all possible combinations. Let's see how bitmasks literally give us a key to unlock every single possible subset of a collection. So, for any set with n items, there are 2 to the power of n possible subsets. And this number, it grows terrifyingly fast. With just 20 items, you're looking at over 1 million combinations. With 30 items, it's over 1 billion. How on earth could you possibly check them all? So here's the classic challenge in computer science. How do we write code that can systematically visit every single one of these millions or even billions of combinations? I mean, the traditional way involves messy, complex, recursive functions that are a nightmare to write and even worse to debug. The Bitmask solution is so simple, it honestly feels like you're cheating. You just write a single for loop. You take a number, let's call it I, and you just loop it from 0 all the way up to 2 to the n minus 1. Now, think about what happens as I counts up. 0, 1, 2, 3, 4. In binary, those numbers are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. The loop is naturally generating every single possible combination of bits for us. And since we already know each bit pattern is a unique subset, this simple loop effortlessly visits every single combination.
And that is the huge aha moment. A problem that feels like it should demand some incredibly complex logic, exploring 1 million different paths, is completely solved by just counting. That's it. This one insight is the foundation for solving an enormous class of advanced algorithmic problems.
Okay, so this technique is obviously incredibly powerful, but let's be clear, it is not a silver bullet. A good engineer knows that every tool is designed for a specific job. So let's talk about the practical applications, and just as important, the trade-offs. So where do you see this stuff out in the wild? Well, you'll find Bitmasks at the heart of solutions for so many classic problems. They're a key tool in dynamic programming, where you need to track which subproblems you've already solved. They're essential in some famously hard graph problems, like the traveling salesperson problem. And they pop up in everything, from scheduling to systems that need to track which features a user has turned on. And here is the single most important rule to remember. Bitmasks are absolutely brilliant when your total universe of items is small and fixed, usually 64 or less. Why 64? Because modern computers are built to handle 64-bit numbers with incredible efficiency. But the moment your number of items gets large, or you don't even know how many there will be, this technique completely breaks down. That exponential growth we talked about suddenly becomes your worst enemy. It's all about knowing the limits of your tools.
And please, don't dismiss this as just some obscure, low-level trick. The core principle, encoding a whole set of options into a single number, is everywhere. It's in the configuration flags for the software you use, the control signals in hardware, and even in how AI models can represent complex states. This fundamental idea of efficient representation is absolutely timeless.
So where do we go from here? We've built up the theory, we've got the tool. In our very next explainer, we're going to put it to work. We'll take this Bitmask technique and apply it step by step to solve some real combinatorial problems, showing you exactly how this magic leads to clean, powerful, and efficient code. So we'll leave you with this final thought, which really is the core lesson today. When structure is encoded correctly, algorithms become simpler and clearer. The Bitmask is the perfect example. It shows how picking the right way to represent your data can transform a really messy problem into something surprisingly elegant. This is K11 Tech University. See you in the next lecture.